Hello, I'm Sue Nelson and welcome to the Create the Future podcast, brought to you by the Queen Elizabeth Prize for Engineering, celebrating engineering visionaries and inspiring creative minds. Today's podcast is rather special as it features the winner of the 2022 Queen Elizabeth Prize for Engineering, an engineer from Japan whose innovation has changed and improved the way we live in so many ways. Dr. Masato Sagawa invented a high-strength permanent magnet that is ubiquitous, but whose presence in everyday devices is usually hidden. Before we hear from the winner himself, here's what a few of the prestigious judges on the panel had to say about Dr. Sagawa and his achievement.
Magnets have existed in the 18th century. So Dr. Sagawa discovered a way to make magnets a lot more affordable and a lot more powerful.
This particular magnet is essentially made from a type of metal called neodymium, which is what's known as a rare earth metal. And it has the property that it can be magnetized, but by itself, it's not stable. The magnetism isn't reliable enough, but mix it with other elements, in this case with iron and the element boron, and you get this neodymium-iron-boron magnet, which is hugely versatile.
This is one of those incredible jewels that sits inside other things. And without magnets, and without these really powerful, small, efficient magnets, we wouldn't be able to have around us an enormous number of things that we take for granted every day.
It's used in MRI for medical imaging. It's used in industrial robots. It's used in the motors that make the hard disks of computers work. It's used in wind turbines. It's used to produce incredibly powerful electric vehicles. The little speakers in your phone, the speakers in your laptop, the motors that last for ages and ages and ages in those portable vacuum cleaners, they're enabled by this kind of high-strength permanent magnet.
Motors lie at the heart of the transition to electric and hybrid electric vehicles. And therefore, the ability to deliver that transition to electric vehicles is hugely important.
He went from the invention to the development to the manufacturing. And that is, I think, sort of the epitome of the highest level of engineering.
You heard there judges Ilya Marotta, who led the Panama Canal expansion project, physicist and broadcaster Professor Jim Al-Khalili, Paul Westbury from the Madison Square Garden Company, Australia's former chief scientist, engineer Dr. Alan Finkel, chairman of the judges, Professor Lynn Gladden, and president of the US National Academy of Engineering, John Anderson. Now, on to the winner himself. Dr. Sagawa has a degree and master's in electrical engineering, and in 1971 he went on to gain a doctoral degree in materials science. He began working on the challenge of creating a new magnet privately while working for an electronics company before leaving to join Sumitomo Special Metals Company. A few months later, in 1982, he announced a new high-performance permanent magnet and in 1988 founded his own company, Intermetallics. Speaking via a translator, I began by asking Dr. Sagawa how he felt about winning the 2022 Queen Elizabeth Prize for Engineering.
I feel very happy and honored to have received such a prestigious engineering prize, and I have nothing but respect and gratitude to the people of the UK for having such an award.
Now, your work has changed the world we live in. Do you ever reflect on what a difference you've made to so many people's lives?
After I have made my announcements of my finding, I found that all across the world who are in the field of magnets, and not only magnets, but magnetism, have come forward with the academics to give me some accolade in regards to my findings. And through that, I started receiving invitations to hold lectures at international conferences. And not only that, a lot of the magnet manufacturers have also invited me to their premises to visit their factories and plants. And a lot of the people who are working in those manufacturers have also expressed their gratitude.
That's lovely. Is there an application of your work that's surprised you or perhaps pleased you the most?
What I found surprising the most is in the area of hard disk. And before the invention of the neodymium magnets, they've had to have magnets that weighed 30 kilograms, which you couldn't possibly carry around. But because of the invention, we've been able to have the same performance through neodymium magnets that you can carry in the palm of your hand. So that's one happy outcome through the invention of the neodymium magnets. And then another one is in the area of air conditioning. And because of the invention of the magnet, the efficiency of the air conditioners have increased greatly, halving the electrical consumption. And this has been now widely adapted around the world. I don't know how it is in Europe. Japan certainly is very hot, so there will be a use of air conditioning. And perhaps in Europe, maybe it's not so hot, so it won't be used as much. But I'm really happy that this outcome has turned the magnet to be used widely across the world.
And when did your interest in permanent magnets begin?
私は大学院の博士課程を出て会社に入ってから My interest really started after I've had my PhD at the university. I joined a company, and after a few years, I got a role to try and improve the strong magnet that was available. And the magnet then was samarium cobalt. So that was really when I started taking interest in these permanent magnets. 興味を持つようになりました。
Why did these magnets need improving then? What were their limitations?
サマリウムコバルト磁石の問題点は、コバルト The issues with the samarium cobalt magnets is that we had to use a substantial amount of cobalt in those magnets, up to about 70% of the total. And that also lends itself to its availability in resource because it was very scarce. And the second point is that if you have a look at the magnetic moment of cobalt, this is substantially smaller than what you would see for iron. The cobalt magnetic moment is 70% less than iron. So we knew that if we could use iron, we would have a much better magnet, but we didn't know how to address this issue.
So what were the engineering challenges then for producing a stronger permanent magnet?
First of all, if we had a look at the samarium cobalt, the samarium part is the rare earth portion. And what I needed to do was to find the rare earth and iron compound, which would be appropriate for a magnet, because the rare earth portion didn't have to be samarium. There are 17 types of those. But I just needed to find the iron being the main component with a combination of another rare earth. So that's what I needed to find. Plus, the second point was that having this compound as the main component, we would need to have this compound have a microstructure and give it an alloy construction that's appropriate for magnets. Furthermore, I had to find out a way to how to produce those magnets and compounds that I would find.
And how did you go about solving these problems?
まず、What I needed to do was to find a good compound between rare earth and iron. And I had also known that the existing rare earth and iron compounds were not good. And at the time, I was able to attend a lecture which touched upon why the currently available rare earth iron compounds were not good. And there, the lecture stated that because the interatomic distances between the iron atoms were too small, and that's why it wasn't giving the magnetic performance that it needed. But if there was a way to increase the interatomic difference between the iron atoms, then this will give a substantial improvement to the magnetism. I took that as a hint, and I started looking into introducing atoms and elements like carbon and boron in between the iron to iron atoms because they had a small atomic radius, and try to come up with a compound which has these carbon and boron atoms to make it into a more appropriate magnet. And taking that as the initiative, I started performing experiments repeatedly. And after going through such endeavors, I was able to discover the compound.
すいません。もう一つ今の
And I just want to supplement from what I said previously. I discovered the compound within a year, but what I also needed to do to make it into an appropriate magnet was to have the appropriate microstructure of the compound to make it into an appropriate material for magnet. And I went into also trial and error after discovering the compound, and it took me another 3 years to come to that alloy microstructure.
And it involved something known as a sintering process that you used. Could you explain this process and why it was different?
私はネオジム鉄ボロンのいい化合物を
I had discovered the neodymium-iron-boron compound, and I was able to make alloy microstructure with this compound. But in the process, I had known that sintering might be appropriate for making this magnet. And through a series of trial and errors and trying to come up with the best composition. Why sintering is good? Well, if I go through the process, first we have the alloy, and then we pulverize it, and then we put it through a metal die. We press the material in a vacuum, and then we heat it up, which gives you a sintered body, and then that turns into the best appropriate neodymium magnet. And it is a process which is pretty similar to what was used for the samarium cobalt magnet. But the composition of the neodymium-iron-boron is 31% neodymium, 61% iron, and 1% boron. And we came up with this composition after a series of trial and errors. But after having come up with this composition, we were able to create the world's number one magnet, and we filed for the patent in July of 1982.
And how did this new magnet compare to existing permanent magnets? What made them so much stronger and better than the ones that had been around up until then?
ネオジム鉄ボロン磁石は、それまでの
The new magnet that we come up with is really strong, and if you compare it with what was available then, the strongest magnet was the samarium cobalt. And what's important to know is that the main constituent is the iron, and the advantage over the samarium cobalt is that it's much cheaper to get the iron. So the magnet itself will be much, much cheaper. Will be readily available. And the second point is that the iron has a much larger magnetic moment. So any magnet that's made from iron has a magnetic property 1.5 to twice better than the samarium cobalt magnets. And the neodymium that's in the compound is quite elastic in nature. So the magnet resulting from that has very high durability.
The judges were also impressed, not just by the engineering and technology advances that this new permanent magnet enabled, but also the tenacity that Dr. Sagawa had in order to get it produced. He's now worked on permanent magnets for 40 years and continues to do so. And this is what the judges, former VP of IBM Research, Josephine Cheng, Amazon's research manager, Abdigani Duraya, and the chairman of India's National Innovation Foundation, Dr. Ramesh Roshelkar had to say.
To me, he's an icon. To me, he's a role model. And the reason is a very simple one. You know, in life, what matters is purpose, perseverance, and passion.
The prize for Dr. Sagawa represents a long journey of innovation from discovery to resolving all the problems with a lot of innovation to manufacturing. And that whole journey is really amazing.
And I think what really speaks to me is his perseverance and decades worth of experimentation, trial and error, and his commitment. And I think it's a great lesson for many of us, especially those who are looking for a career in engineering and science.
Now, we heard several of the judges admiring your perseverance in getting your innovation made and then manufactured on a large scale. What qualities do you think an engineer needs to have in order to be successful?
はい、それは私は実験することが好きなんですね。
I would say that I really like experiments and I really like making samples and repeating those experiments. Whatever substance I have at hand or materials, I would think about how those materials are working inside my head. I would perform experiments, and once I come to a viable idea, then I try to make samples and measure what we can do with those materials. And I really like this cycle of making samples and measures. And I think that was one of the keys that led me to my success.
一つの成功の原因だと思います。
What's your future aim for neodymium magnets?
私はこの大道で、今
Currently, I'm consulting for Daido Steel, and what I'm working on is the neodymium magnets that will be used for the traction motor that's to be used in the electric vehicles. And I'm involved in the research together with the team. And our goal is that the current neodymium magnet uses an element called dysprosium. And we want to have the magnet use less of this element to improve its performance. And what we want to do eventually is to have a battery used for electric vehicles, which has the world's highest performance in magnetic properties, and find a way for us to produce them in factories. So I'm getting together with Daido Steel with the aim of trying to achieve this magnet to be used in electric vehicles and to be mass produced.
Is there another potential application for your magnet?
What I want to do is to have the neodymium magnets to be used in the motors of the electric vehicles across the world. And we can foresee that there will be more electric vehicles across the world. And we're hoping that all of those will eventually have the neodymium magnets that they use in the electric vehicles.
What's your advice for young engineers or anyone considering a career in engineering?
私は若いエンジニアに
What I would say to the younger engineers is to have a look around you, and there are needs that are within society, what people need. There are those needs that are unmet. Find those and try to think of a way to find solutions and realize that, and think over how and what you can do. Try to come up with some kind of idea, because if you can get this idea, then that can become a research theme, and it will be something that would be worthwhile for your research. When you do that though, try to set a concrete goal on how to try and achieve that. And when you try to think about how to try to achieve that, then you'll come up with many more ideas. So keep thinking. And once you get these ideas, experiment and try to realize those goals. Because once you are able to go through, there will be a moment when you thought, I am so happy that I went through the engineering journey and became an engineer. There's no greater joy in the world. And so I'm hoping that the younger engineers can pursue this kind of path and become such a researcher and engineer.
Dr. Masato Sagawa, thank you for joining us.
Thank you very much.
On the Create the Future podcast. And thank you to Yosuke Shinokubo for translating.
Thank you.
Find out more about the Queen Elizabeth Prize for Engineering by following QEPrize on Twitter and Instagram, or visit QEPrize.org. Thanks for listening, and join me again next time.